Hello and welcome to section 5.4 live from my office in Chateau de Paron. Hopefully you're someplace nice and cozy and we can go over a few problems from this section. It's just some extra work with integrating and trying to find antiderivatives and using those antiderivatives to find the value of a definite integral. We'll start out with this particular problem, problem number 10. And we're going to try and work to find the antiderivative here. Now, in a lot of cases, you're going to have to work with the integrand to rearrange it to make it something that you can integrate. And in this case, I'm going to treat that x to the square root of x is x to the 1/2, and it has to distribute itself to all three of these terms here. So when I add 1/2 to these exponents, I get this expression over here to the right. Now, integrating is the opposite of differentiating, so what you're going to do is add 1 to the exponent and divide by that same exponent. Now, I left them here as decimals, but that's only going to go so far because I don't think decimals are going to fly when it comes to putting in your answer into WebAssign. In any case, I get x to the 3.5 divided by 3.5 and so on down the line. Try not to do too much at this one step. Just add 1 to the exponent and divide by that same exponent. Now from there, I said, you know what? I realized that I'm going to have to work with these things as fractions. So I wrote numbers like 3.5 as a fraction, 7/2. And again, these match, that's good. When you divide by a fraction, the trick is to invert and multiply. So dividing by 7/2 is like multiplying by 2/7 and so on. Dividing by 5/2 is like multiplying by 2/5. 2/5 times 3 is 6/5. 6/5 x to the 5/2. And then finally plus 4/3 x to the 3/2 plus a constant. So yay, that's our final answer. Now just a quick question here for you. If you're curious, if you're looking at that and saying, you know, I'm not so sure I'm right on that, how could you check your final answer here? If you said differentiation, you're right. And you differentiate it, and you should get the integrand here, that is what's underlined in red. And then, of course, you can factor out an x to the 0.5 from there and get what we started out with. Cool. Let's try another one. Let me move up a little bit. Kind of like problem number 10, before you get going on problem number 11, you've got to rearrange it because we can't integrate a quotient like that. There's no quotient rule for integrals. There's no product rule for integrals. Not at least in the sense that you're familiar with the product rule and quotient rule from earlier when we were dealing with differentiation. So to start this one, I'm going to take and divide everything through by x. And when I do that, I'll then simplify things. I'll think of the x in the numerator of that second term as x to the 1/2, and then you just divide exponents. In fact, I did that work right here. X to the 1/2 divided by x to the first power. Well, subtract exponents, that gives me x to the negative 1/2. And the last term here, x over x is just 1. So the antiderivative of this will do piece at a time. It starts out here. What do you differentiate to get 1 over x? 1 over x is a derivative of what function? Is anyone out there that can help me out? Yeah, Jeff. Yes, that's correct. Natural log of x. Well done. Natural log of the absolute value of x, to be precise. And up here, we'll add 1 to the exponent. So negative 1/2 plus 1 is positive 1/2, and divide by that same exponent. See, again, I'm not trying to do too much at that one step. Try and do too much, you could get it wrong. The antiderivative of 1 is just x. Now, how come I don't write r or s or t? It's because I'm integrating with respect to x. So the antiderivative has to be something in x that'll differentiate to 1. Plus your constant, we clean up that middle term here a little bit, and we have a nice expression down here at the end. Now you could write that 2 to the 1/2 as the square root of x there, or 2 times the square root of x. That's fine. It's not really a big deal to me, but it sometimes might be the difference between getting something right and wrong on WebAssign because it tends to be a little bit picky. Cool. Let's work with one more indefinite integral. Now, why am I saying indefinite? Well, it's an indefinite integral if there's no limits of integration. So there's no lower to upper limit here. So, okay. Now, like the previous couple of problems, we can't just jump right into the integration. You're going to have to do a little bit of thinking first. And that little thinking is this. We're going to distribute this here and here because that gives me an integrand which I think it's a little bit easier to work with. In fact, you should know the antiderivative of secant squared and of secant x tangent x. That is, what do I differentiate to get each of these terms? So let me throw it out to, okay, Jeff, what is it? Yes, thank you. So it'd be the tangent of x plus the secant of x plus, yes, Jeff, thank you, yes, plus c. It's our constant of integration. Please don't forget that. That is something that tends to cost you a point, and neither of us are happy about that. Okay, so those are some examples of indefinite integrals. Notice that in each case we had to manipulate the integrand. The integrand, of course, is what you're taking the integral of. So it's that part right there. It's this part right here, etc. You might have to manipulate that to get it into a form that you can find an antiderivative. Now in section 5.5, we'll learn even more tricks to finding antiderivatives. We'll be doing a U substitution. But for now, let's move up to the problem of finding a definite integral. So this could be interpreted as finding the area between 1 and 4 underneath this curve and above the x-axis. Just like some of our previous ones, we're going to start out by manipulating this. I'm going to divide each term in the numerator by this term in the denominator, and I'm going to think of that as u to the 1/2 power. So rewriting it and then doing some division, 1 minus 1/2 gives me 6u to the 1/2. Here I'll just write that as 4u to the 1/2. Now what you should expect and what we're going to do is add 1 to the exponents. So I'll add 1 here, that gives me u to the 1/2 divided by that same exponent. And then likewise u to the 3/2 divided by the same exponent. If you invert and multiply, we'll multiply 4 by the reciprocal here, so 4 times 2 over 1 is 8. 6 times 2 over 3 is going to be 4, because the 3 will cancel, and you'll be left with 2 times 2. Notice that I went from an integral symbol to a straight bar. And the reason for the straight bar is that we're done with the antiderivative. We already found it. So please don't write integral here, write a straight bar. And that notation means you're going to plug in, first of all, the upper limit, that is the 4. So I'll plug in that 4 into the function here and here. I did that over here. And then evaluate it. Likewise, we're going to plug in the 1 in here and here. And you can kind of see that. You can see where I plugged it in orange to the right. So right here and here. Now it's up to you. Some of you aren't necessarily going to be the fastest with working 4 to the 3/2 power in your head, and that's fine. So if you wanted to, one way to finish up this part here at the end is do this. Plug in that function into your equation editor, which I did here. And then assuming that you've set things up in terms of your table so that you have things set to ask for the independent, you can go to graph and then just type in the numbers that you need. So at 4, the value of the function is 48, and at 1, the value of the function is at 12. Perfect. It's exactly what we're looking for. So this turned out to be 48, that turned out to be 12, and guess what? The difference is 36. Nice. Okay, questions? Yes, Jeff. Why didn't we need a constant of integration here? Well, we could have a constant of integration here, but watch what would happen. If I had that constant of integration here, then when I plugged in 4 in my upper limit, I'd also have plus c here. And then when I plugged in 1 for my lower limit, I'd have a plus c here. And that c here and that c here are going to cancel when we do our subtraction. So basically, you can put it in, but it's not going to make any difference. So generally speaking, we just leave it out. And with all your indefinite integrals, I strongly suggest that you just leave it out. Don't bother to put it in the first place. Cool. Hey, thanks for the question. All right, couple more. You might need to dig back into your notes a little bit to find this one. Now, maybe it's something you need to do, maybe it's not, but since 4 doesn't depend on our variable of integration at all, I'm going to take 4 and put it out in front. That'll leave me with 1 over 1 plus p squared times dp, and I just move that dp up into the numerator there, just out of convenience there. It's not a big deal. You don't have to do that. That's fine. But this part here hopefully looks a little bit familiar. That's the derivative of the arctan. So some people might write it as arctan. Actually, it should be of p. Other people will write it as tangent inverse, tan negative 1. It's up to you. I did have one of my students get marked wrong because she used tangent inverse and they were expecting arctan or vice versa. I can't remember which. So just be aware that these two are equivalent. Look for it on any palettes that help you answer your problems. Now, see, 4 tangent inverse of p. Plug in your upper and lower limits. So I get the arctan of 1 minus the arctan of 0. Well, what angle has a tangent of 1? If you said 45 degrees, that's great. If that's not coming to mind very easily, that's okay. You probably would want to set your calculator in radian mode. So let me just clear this out a little bit. There we go. So I'm going to go down and set it in radian mode. Excuse me, degree mode. I know calculus is done in radians. Let's exit out of there. Inverse tangent of 1 is 45 degrees. Oh, okay, yeah. Of course, we need our answer in radians. So that's going to be pi over 4. So you can check yourself if you'd like. You can compare this to the answer that I would have gotten had I been in radians. So let's try this again in radians. And I should get the same decimal answer, and I do. One way or another, you're going to be responsible for figuring out what that is in radians. So that gives me my pi over 4 here. Inverse tangent of 0 is 0. And when I distribute the 4, I just end up with pi. Okay. Last but not least, problem number 37. So you might notice a little theme here. What I'm trying to do is emphasize that sometimes you need to manipulate the integrand, that is that stuff that I put in the parentheses, in order to be able to find an antiderivative. We've seen a couple times today where we divide each term in the numerator by the term in the denominator. And that's the trick in problem number 37. Being very helpful, I'll do this part here for us. Cosine squared over cosine squared is 1. But can someone help me out here? What's 1 over cosine squared? Anyone? Anyone? Come on, somebody other than Jeff. Okay, Jeff, can you help me out one last time? Yes, thank you. Secant squared of theta plus 1. And what's nice is that we know a function whose derivative is secant squared, and that would be the tangent. Of course, the antiderivative of 1 with respect to theta is going to be theta, and we can plug in our upper and lower limits. At pi over 4, it becomes tangent of pi over 4 plus pi over 4. And unfortunately for us, tangent of 0 and 0 is just 0. Over here, let's work with this. In fact, we were just working with its opposite, so this shouldn't be too bad. What's the tangent of pi over 4? And that's 1. So there's our final answer. Cool. Well, I hope this helps out with the homework. If you have some more questions, please get a hold of me. If not, see ya.
And that's going to involve two things. One is the mean